Alright, in this video we will be discussing sampling distributions. This will be the lecture for our class on 16 April. On this class meeting, come with the notes for this video. Alright, first we'll begin with a reminder of one of the big ideas of the course of statistics. We have two concepts that we've discussed regularly. One, the idea of a population. A population is some large set that we will look to describe. Maybe the population is the entire world. Maybe the population is U.S. women. Maybe the population is the citizens of Jacksonville. So typically the population is a large set that we are not going to be able to examine entirely. Alright, so we'll look at some small part of that set. Well, that small part, this little element here, that we're going to take out and look at a little bit closer. Alright, this is a sample. Okay, sample. And we can look closely at this sample. It may be a very small part of this population. It may be a relatively large part. Well, we can look at that sample and make some judgments about the population. Well, numbers that describe the population, we refer to them as parameters. From the population come parameters. And numbers that describe the sample, they are called statistics. Alright, population, parameters, sample, statistics. The culminating concept in statistics is using information about the sample to make some judgment about the population. And this situation where we take something from the sample and make a judgment about the population is called inference. And that's the final thing we're going to be learning how to do in statistics, inference. Inference is a conclusion with confidence. Conclusion with confidence. And by confidence, I don't mean, yeah, we feel good about it. I mean quantifiable, as in we're going to say we are 90% confident or 95% confident. We're going to be able to quantify how certain we are about this conclusion. That's what separates statistics from inference that you've talked about previously. In stats, we're going to place a number on how certain we are about our conclusion. Okay. So let's talk about two of the key numbers that we've discussed throughout the course. All right, again, we have parameter. All right, and a parameter is a number from the population, a number that describes the population. And we have statistic. And that's a number from the sample. Okay. Well, the two key numbers that we've talked about and we'll continue to talk about as we move into inference: mean and proportion. Okay. For mean, the parameter, we use the Greek letter mu, like a little cursive sort of U looking character, and that's not the best mu that ever existed, but it'll be okay. Its statistic brother is x bar. This is the sample mean. This is the population mean. Alright, for proportion, the parameter is p. The sample version is p hat. They should all be that easy. Alright, let's look at a couple of concrete examples of this. An example of both of these. Example, and this is going to be for means. Assume the height of adult U.S. women is 64.5 inches, 5 foot 4.5. All right, we were given that earlier in the year in the problem. We take an SRS of 4 women. Their heights are, divided as a set, 66, 64, 70, 60. Okay. The mean of this group is 65. All right. So, looking at our terms that we had before, assume the height of adult U.S. women. This here is our population. This is the group we're trying to talk about. Okay. Is 64.5 inches. Well, this is a number that addresses the population. This is a parameter. And since we're talking about mean, we say this is mu. In this case, mu is 64.5. This is our population mean. And very frequently, we don't know what it is. We're making an assumption based on previous data or lots and lots of measurements, or it's just given to us. So this mu, this is our population mean. All adult U.S. women have a mean height of 64.5. Did we go out there and measure every single woman and know that? No. Were you measured by these people? Probably not. So this number here could be just an assumption, could be based on some good, lots and lots of samples, but bottom line, it is the population parameter. It is our population mean, mu. Okay. We take an SRS. Remember, this is simple random sample. Simple random sample of 4 women. Their heights are this, and this. If we find the mean, it is 65. This is X bar. This number came from our sample. It is a statistic. It is the sample mean, X bar. If I add these numbers together and divide by the number of numbers, you would see that it's indeed 65. Okay. We could do a similar situation for proportion. For instance, we might assume that 30% of people have attended church in the last month in the entire state. Well, if I go out there and ask 10 people, did you attend church? And 4 of them say yes, well, that is our sample statistic, p hat, 4 out of the 10 that we asked. Okay, so in the same way that we see mean, the population in the sample, we can see proportion, the population in the sample as well. Okay, proportion typically we're thinking of as a percent. All right. Now we're going to revisit types of distributions we've talked about. Types of distribution. Distribution. Types of distributions. All right. First, we've talked about the population. And the distribution of the population could take on a lot of different forms. Typically, we're considering some kind of density curve or histogram that describes the way the entire population occurs. All right. The next kind of distribution we've looked at is the sample distribution. That is, when we take, as we talked about before, a part of this population and look at the sample, we can see specifically how these 4 or 6 or however many break down. With regards to our previous example, the heights of U.S. women, they're going to be normally distributed, but these 4 women we took here, 66, 64, 70, 60, they're just 4 little data points. So in this particular case, the sample distribution is simply these 4 points we have here. The population distribution would be a density curve, and indeed it would be normally distributed. All right. Lastly, what we're going to be looking at now is called a sampling, I-N-G, sampling distribution. And what a sampling distribution is just like the name would imply, it's a distribution of samples. So in our problem here, we took this one sample of size 4. What would this look like if we continually took samples of size 4 and plotted them? Well, we're going to get an idea of what that might look like here in a second. I'm referencing an online applet. I'm going to show you where you can find this. All right. As you can see in the bar here, it's onlinestatbook.com. Onlinestatbook.com. If you simply Google sampling distribution applet, sampling distribution applet, and the very first hit is going to be sampling distributions, online statistics. All right. You can click begin here. Okay. Now I'm going to discuss what you see now. This top graph is the parent population. This is our population distribution. And you can make this look, if you just hold down your mouse, you can make it look like anything you want to. I can make a distribution that is very, we would say here, right skewed. You see the tail is to the right. Okay. Or we could make one that is very left skewed. Get over here and eliminate this. Alright, that's left skewed. Here you can set it on things. Uniform, that's like a rectangle. Okay. Here's a skew, they make us a skewed one. Alright, our custom here, we're just going to paint one. Alright, something that we call this bimodal. There's 2 peaks. Alright, it's kind of crazy looking. So this is the parent population, or just population. All right, and this area is going to be the sample data. That is, we're taking parts of this population. And lastly, you see distribution of means. This is our sampling distribution. Okay, so let's take a look at what happens when we have a normal situation. Well, here's our normal population, much like our heights that we're just talking about. All right, and I'm going to look at a sample. Here it says n equal 5. I can change this to whatever I want. 5 is fine. Okay. I'm going to hit animate. In this area here, this 1, 2, 3, 4, 5, this is our sample. This observation here is the mean of these. That is, they added 1, 2, 3, 4, 5 together, and they found where that is. You can see this observation would be the mean of all those. I'm going to do it again. So they have randomly sampled from this, and this is 1, 2, 3, 4, 5 observations. They've averaged those, and they've put it here. This is the population, this is the sample, and this is the sampling distribution. It's a distribution of these sample means. And you could imagine, since this thing is normal, that this distribution here is going to be normal as well. And I'm going to go ahead and throw 10,000 of them in here, and we'll take a look. You see, this distribution is normal, and this one is too. But one thing I hope you notice is this one is much less spread out. Here you can see the standard deviation. The standard deviation of our initial population is 5, but the standard deviation of our sampling distribution is 2.23. It's less spread out. That makes sense. Since we're taking samples of size 5, it's going to even out, or we're less likely to get 5 observations from the tails. You're going to get more observations in the middle, so naturally it's going to be spread much less. Imagine if we took the whole population, well then the observation would be right here on the mean, so it makes sense that this is going to be less spread out. But curiously, if this is not normal, like I'm going to go skewed, okay? In fact, I'm going to make it even more skewed. Make it real dense to the left and very little in this direction. Alright, now we're going to look at samples of size 5. We'll go in here, and samples of size 20 are going to go down here. So we're doing 2 sampling distributions at once. Here's 5. Here comes my mean, and now is going to come 25. I hope. Here I go. One more time. Go. Here's 5. There's my mean. Here comes 20. I meant 20 here. And it's going to deposit the mean down here somewhere. Alright, there it is. I'm going to go ahead and do 5 of these, and we can see where this thing is headed. Alright, you can see that this distribution here of size 5, it is somewhat skewed, but this one of size 20 is starting to look fairly normal. Here I'm going to hit 10,000. We can see where we end. Here this thing is still a little right skewed, but we see our distribution down here is fairly normal. Depositing 100,000, still a little right skewed, still fairly normal. So what we see is no matter what this parent population looks like, these sampling distributions tend towards normal as the sample size gets larger.